Hi everybody, and welcome to Lesson 2.9, Renewable Energy. The content in this video is aligned to the third edition of Environmental Science for AP and covers information from College Board Units 6.7 through 6.12. We are continuing on our deeper dive into a variety of energy generation sources and processes. Here we'll be discussing various renewable energy sources. This leads us to the content objective of understanding that humans use energy from a variety of sources, resulting in positive and negative consequences. By the end of this lesson, you should be able to describe the use of the following in energy generation: biomass, solar energy, hydroelectricity, geothermal energy, hydrogen fuel cells, and wind energy. You should also be able to describe the effects of each of these sources in power generation on the environment. This leads us to being able to answer our guiding question: how do we shift to renewable energies? Let us begin with biomass. We know that biomass is anything that was once a living thing. It is based on carbon, just like fossil fuels. When we think about biomass, we typically think about wood. And while wood is still one of the most abundantly used biomass sources in the world, it is not the only one. Crop waste, like corn stalks and garbage, can be types of biomass that are used for a variety of purposes. Garbage, for example, undergoes decomposition and releases methane. This gas can be trapped in landfills and piped to a power station to be burned to produce electricity. This is an example of cogeneration, where the waste products of one process are used in a secondary way to produce energy. We also have alcohol fuels, such as ethanol, that can be used to replace gasoline in some cars. Here we see the steps of producing electricity from the burning of biomass. If you look closely, you'll see that several of these steps are the same as with generating electricity from the other energy sources we have looked at so far. Biomass is burned, which produces heat. The heat is used to boil water. The boiling water produces steam, which is collected and funneled through a narrow pipe. The narrow pipe forces the steam under pressure, increasing its force as it is released onto a turbine. The turbine spins, which produces mechanical energy. The turbine is connected to a generator, which takes the mechanical energy of the spinning turbine and converts it into electrical energy, which can then be released onto our electrical grid. Biomass does have multiple benefits as a renewable energy source. It is renewable and, when managed sustainably, can be a carbon neutral energy source. To be carbon neutral means that the amount of carbon being released from the energy source in all steps of the process is the same as the amount of carbon sequestered in the source itself. In some cases, particularly businesses, carbon emissions can be offset in other means, such as replanting trees that will eventually sequester the same amount of carbon that was released during the process itself. One of the major problems with using biomass as an energy source is the problem of incomplete combustion. Complete combustion means that all components of the original energy source are converted into final products. For something like a fossil fuel, whose basic components are carbon, hydrogen, and oxygen, complete combustion means that all the carbon, hydrogen, and oxygen in the fossil fuel, a hydrocarbon, are converted into the end products of carbon dioxide and water. There is little to no unused matter left behind. Incomplete combustion occurs in an environment devoid of enough oxygen, which leads to some of the components not going through the burning process. This process produces water, carbon monoxide, particulate matter, often in the form of ash or soot, and volatile organic compounds. The products of incomplete combustion are all major air pollutants and have significant human health effects, such as dizziness, nausea, vomiting, confusion, respiratory illness and distress, mental retardation, and even death. While biomass is a renewable energy source, it does carry with it a variety of environmental impacts. As we've already seen, the combustion process, whether complete or incomplete, creates issues like carbon dioxide and carbon monoxide emissions, the release of particulate matter, and volatile organic compounds into the atmosphere. These have dramatic consequences for human health and for global climate change. The focus on biomass as a fuel source can also lead to the use of agricultural practices that negatively impact surrounding ecosystems. Monocropping and excessive timber harvesting can lead to topsoil loss, nutrient depletion, deforestation, and habitat loss. And while there are no direct water impacts for burning biomass, the use of fertilizers and pesticides for growing them on an industrial scale can have impacts such as cultural eutrophication. Solar energy comes from the visible light that is released from the sun as part of the electromagnetic spectrum. The energy in these photons can be used for many things based on the method of capture of those photons. When we typically think of solar energy, we think of what are known as photovoltaic or PV cells or solar panels. These are the hallmarks of active solar energy use. Active solar energy use requires that the energy be converted from the photons into something else, such as electricity or indirect heating of water. Passive solar energy uses the design conditions of buildings to make effective use of incoming solar radiation for things such as natural light and heating through the use of insulation or other building materials. Solar energy can also be used for cooking in parabolic solar ovens, which are often used in camping and other potential off-the-grid behavior. The use of solar energy to produce electricity is done exclusively through the use of PV panels. PV panels are essentially two semiconductors with a junction between them. Each semiconductor is connected to an electrode with a particular electric charge. These semiconductors are beneath a layer of glass with anti-reflective coating, which is designed to ensure that as many of the photons as possible are engaged during the process. Photons are absorbed into the top semiconductor, where electrons are knocked loose. These electrons flow through the junction between the conductors, creating an electrical current. This current is the actual electricity produced from the PV cell, which is moved off onto the electrical grid of the house, building, or onto the actual electric grid. A single solar panel is made up of, at a minimum, of 60 different PV cells. Current PV technology makes the conversion of photon energy to electrical energy at a rate of between 15 and 18% efficiency. However, technology for these PV cells continues to grow exponentially, meaning that it is highly likely that panels will need to be changed out relatively often to function with the highest efficiency. Here is another way of viewing the steps of producing electricity from a PV cell. This version is similar to the pathway we've seen before, but shortened, as solar panels do not boil water to produce electricity. The sun radiates energy in the form of photons. Those photons are absorbed by a PV cell. Photons knock electrons loose. Electrons flow across a junction, creating an electric current. The electrical energy is transferred to the building or to the energy grid. One thing to note about solar panels is that they are most efficient in areas of very little shade with the most direct sunlight. Therefore, solar panels should be oriented toward the equator whenever possible. The other major way in which solar energy is used is in heating, either passively or actively. Passive solar heating makes use of specific design choices to maximize the sun's energy usage when it is beneficial and to minimize it when it is not. This can come from the use of overhangs that are specifically sloped to block summer sun, but to allow the winter sun, which sits lower in the sky during its brightest, to enter. Double-paned and insulated windows can keep excess heat out during the summer while retaining heat in the winter. Effective insulation within walls do the same things. Other options for these structures include stone floors and other items that can absorb heat throughout the day and then radiate it back later. Active solar heating is used when the sun's energy actively increases the temperature of something, in most cases water, that is used within the structure via a pump. This pump carries the heated water throughout the structure as needed, often through things like hot water heaters, heat exchangers, and forced steam radiators. The major environmental impacts of using solar energy come from the processes of actually manufacturing and disposing of the panels and their components. The electrical components of the panels must be mined, transported, and manufactured, which requires large amounts of fossil fuels, contributing to emissions of carbon dioxide, sulfur, and nitrogen. The mining process leads to erosion, topsoil loss, and habitat loss. The chemicals used in the manufacturing and functioning of PV cells are hazardous and can leak into the soil during function if damaged and once discarded. Waste management is another issue that affects soil, as the discarded panels must go somewhere, and there are large amounts of useful compounds that could be salvaged for reuse. As with soil, chemicals from the production and use of the panels can be released into water supplies if they are not carefully maintained and properly disposed of. Hydroelectric energy is used almost exclusively now for the production of electricity. There are several different types of hydroelectric energy generation. Here we will briefly discuss the types and their differences. Nearly all of them make use of turbines to convert mechanical to electrical energy. Most people would be familiar with a storage hydropower plant. This type of plant is built to create an artificial reservoir behind the dam. The water is allowed to move through the dam in set intervals and quantities based on the region's local conditions and rainfall, the flow rate of the river feeding the reservoir, and the energy needs of the power company and surrounding region. Pumped storage hydropower requires the use of a pump to move water from a lower lying area to a higher elevation, at which point it is put back through a turbine into the lower pool. While this does require energy to pump the water uphill, additional changes can be made in the backflow to generate a net gain in energy. Run-of-river hydropower places a turbine or a set of turbines in the flow of a river, typically in the portion with the swiftest and most consistent flow, to ensure the maximum amount of energy generation on the most consistent basis. Tidal power makes use of turbines that have bidirectional spin. These turbines are placed on an area near a continental shelf or coastline. As the tide comes in, it spins the turbines in one direction. Motors then turn the turbines around prior to the tide leaving, where it turns the turbines again. Lastly, wave power makes use of the up and down motion of waves through the use of buoy or paddle generators. These are the basic parts of a traditional storage hydropower dam, the most common type of hydroelectric power generation plant that will be referenced on the AP exam. Let's briefly go over the important components. The physical structure of the dam itself is made up of the concrete structure that contains the intake, penstock, and powerhouse, which includes the turbine and the generator. The intake regulates the flow of water from the reservoir. The penstock carries the water down an increasingly steep incline to the turbine. The flowing water spins the turbine, which allows the generator to produce electricity. Here we see the steps of producing electricity from flowing hydropower. If you look closely, you'll see that several of these steps are the same as with generating electricity from the other energy sources we've looked at so far. The difference here is that we begin with the step of the turbine. Flowing water moves over the turbine, causing the turbine to spin, which produces mechanical energy. The turbine is connected to a generator, which takes that mechanical energy and turns it into electrical energy, which can then be released onto the electrical grid. Wave energy produces energy in a similar manner, but rather than using water turning a turbine, it is through the up and down motion that produces the mechanical energy that is converted into the electrical energy. Hydropower produces impacts on the environment in a variety of ways. Major atmospheric impacts occur during the construction of the hydroelectric dam or plant. This requires large amounts of fossil fuels for production, transportation, and construction of components, contributing to emissions of carbon dioxide, sulfur, and nitrogen. The construction process also leads to significant loss of topsoil and habitats, as well as erosion. There are also issues with waste management when it comes to the disposal of the mechanical components, such as generators and turbines. Hydroelectric power plants also significantly disrupt the natural flow of a river. This can lead to the process of siltation or sedimentation, where excessive deposits of silt or other sediments accumulate due to the slowing of the flow of a body of water. Sedimentation happens more quickly in the reservoir area behind the dam. This reduces the volume of the reservoir, leading the water to either spill over its containment and flood the surrounding areas, or to push through the dam itself, potentially corroding components with sediment. Proper management of this process can be maintained, or a dam could suffer catastrophic failure. There is also the issue of habitat disruption in aquatic environments. One notable impact is on migrating fish. Some dams have built what are called fish ladders, which allow migrating fish, such as salmon, to be able to continue their pathway upstream through a series of increasingly elevated jump pools. In many areas, these fish ladders are required by the Anadromous Fish Conservation Act. Anadromous fish, like salmon, are those that live the majority of their lives in saltwater, but mate in freshwater. Geothermal energy, like biomass, is only available in certain areas. Whereas biomass requires the existence of arable soil, water, and sunlight to be effective, geothermal energy is only available in areas of high mantle or tectonic activity. This can be areas like natural hot springs and geysers, or on active volcanic sites. The vast majority of geothermal used in the U.S. is typically for personal home use, where geothermal heat pumps are used to provide radiant heating for homes in cold months and to provide hot water for bathing and cooking. However, areas with large amounts of consistent geothermal activity, like Iceland, can make effective use of geothermal energy for large-scale power production. Here we see the steps of producing electricity from large-scale geothermal energy. If you look closely, you'll see that several of these steps are the same as what we have seen before. Here, the water is forced into the earth, where it is subjected to the convective heat of the upper mantle. This heat is used to boil water. The boiling water produces steam, which is collected and funneled through an increasingly narrower pipe. The narrow pipe forces the steam under pressure, increasing its force until it is released onto a turbine. The turbine spins, producing mechanical energy. The turbine is then connected to a generator, which takes the mechanical energy and converts it to electrical energy, which can then be released onto the electrical grid. Geothermal poses few environmental hazards during its normal functioning. Because heat is being used to boil water and produce steam, one of the major byproducts of using geothermal energy is water vapor. It can also produce sulfur emissions through the use of various chemicals in the fluid that is used to transfer heat. While unlikely, it is possible that subsidence can occur if significant soil or rock disruption occurs. As for water resources, the most likely issue is that of chemical infiltration that can occur from the fluid being used to transfer the heat. Fuel cells are relatively new technology that function to produce energy through the use of various chemical compounds and electric currents. Specifically, hydrogen fuel cells are the most promising of these technologies. They are currently used as a source of backup power in stationary and mobile forms. Additionally, research has been conducted continuously over the past decade into the formation of hydrogen fuel cells that can be a gasoline replacement or supplement to reduce battery production and petroleum use. Hydrogen fuel cells function by forcing hydrogen gas across an anode and oxygen over a cathode. The movement of these gases across these electrical components allow for the formation of water and the transport of electrons across a membrane. This transfer of electrons generates heat and electricity, which can be used as power. The normal output of a hydrogen fuel cell is water. Currently, the major problems with hydrogen fuel cells come from their construction. The components must be mined, transported, and manufactured, which leads to large amounts of fossil fuel use, responsible for excessive carbon dioxide, sulfur, and nitrogen emissions. The electrical components are also manufactured using hazardous materials, which must be appropriately managed through waste management processes. These electrical components also include materials that can be reclaimed through recycling processes and can be used to provide additional access to these materials to reduce the need for mining later. The mining process also produces issues with habitat loss and erosion. Presently, the major issue with water resources comes from the potential of groundwater contamination from the electrical components leaking potential hazardous materials from discard sites. It should also be noted that large amounts of energy are required to produce the hydrogen gas, which is the basis of the hydrogen fuel cell function. Wind power is one of the oldest forms of energy used by humans, right after biomass and running water. Windmills, not to be confused with a wind turbine, have been used for centuries to grind grain efficiently. Wind turbines are used for the sole purpose of producing electricity. Sometimes they are used for small-scale electricity generation in a single town, or even in some areas, a single home. They can also be used for additional supplemental electricity on the traditional electrical grid. A wind turbine is made up of three basic parts: the blades, the nacelle, and the tower. The blades are specially shaped to resemble an airplane wing, with its leading edge wider and the following edge narrower. This design helps with aerodynamics and allows air to move more efficiently across the blade, increasing the amount of energy that can be transferred. A rotor is connected to the blades, which helps to rotate the blades to change the pitch, or the angle at which the blade faces the wind. The pitch can be changed from 0 degrees all the way up to 90 degrees. The rotor can also change the blade location in the event of high winds that could damage the blades and other components of the turbine. It's important to note that the ideal pitch for most wind turbines is around the 15-degree mark. The nacelle is the largest component of the turbine. It is at the top and encases two shafts, a gearbox, and a generator. The shafts and gearbox are used to effectively transfer the mechanical energy from the turbine, which spins relatively slowly, through a junction in the gearbox, increasing the rate of spin to provide as much energy as possible to the generator. From here, the generator produces electricity and transfers it by a series of wires through the tower to its intended target. Here you see the steps of producing electricity from large-scale wind. If you look closely, it's very similar to what we've talked about before, and it's what we've just seen in the previous slide. Temperature differentials in the air produce wind that interact with the turbine. The turbine spins, producing mechanical energy. The turbine is connected to a generator, which converts mechanical energy to electrical energy. The electrical energy is then transferred to the electrical grid. Like solar and hydrogen fuel cells, the vast majority of problems associated with wind power comes from the manufacture and transport of the components. The use of large amounts of fossil fuels, which contribute to those atmospheric pollutants, are required for the mining and transportation of these components. Waste management becomes a problem when the blades are damaged or changed out, as it is difficult to recycle and reclaim fiberglass and other components of the blades. Temporary habitat loss occurs when the turbines are installed, although multiple use of the land is possible and encouraged. Water contamination is an issue with debris from offshore turbines, though these are relatively well maintained, and this is comparatively unlikely. Turbines, unlike many of the other renewable energy resources, have specific impacts on wildlife. Because of their height, it is common for birds and bats to collide with the turbines. In some areas, due to the provisions of the Migratory Bird Act, wind turbines are not allowed at all because they interfere with and pose a danger to the safety of protected birds during their migration pathways. The following slide provides you with an opportunity to see how some of these ideas are connected together. Feel free to pause the video and explore the connections between these topics. Then use the statements at the beginning to review.